We are going to talk about gravitational potential energy in this video. And I'm going to prove that the formula for getting the potential energy of two bodies with mass is by using this formula, negative gmm over r. So in picture, what this looks like is that there is an object with big letter M as its mass. There is another object nearby, and we're using small letter m. It's just notation for the mass of that object, and their center to center distance is r. And of course, these two objects will attract gravitationally because they have mass. And if we treat both objects as part of one system, the two-body system, then these two objects will have a property, and let's call that property gravitational potential energy. And let's give that property a symbol of UG, and its unit is joules. And what else do we know about this? There's one internal force, and that force is the gravitational force. And what else do we know about this? We know that this property is inversely proportional to the center to center distance between them. We know that it is directly proportional to both masses. And we also know that it is negative, and it is always negative. This property is always negative. Why do I say that? Well, mass is always positive. Center to center distance is always positive. This gravitational constant is always positive. You have a positive number multiplied by a negative sign, you're always going to get negative value. And I'm going to try to convince you that the reason why this is negative. Then this is another important idea, that when gravity works, the property will change, but the change is negative. So there is a negative change. We all know, I'm going to draw that object again, the mass and the other mass. We know that they are attracted gravitationally, and because of this gravitational attraction, they will not stay that distance forever. They're gonna draw closer, and I'm gonna try to draw the two objects are closer. So r is smaller. And actually, the gravitational force is also stronger. If you remember the law of universal gravitation, that Fg is inversely proportional to the square of the separation distance. So apparently, this formula tells us that the gravitational force is doing work. And I can see that it really makes sense. Gravitational force is really doing work because it's causing the objects to move, and while the force is applied. And according to this formula, because of this work, the property called UG has now changed, but the change is negative, which means if this is our final setup, that the property for the final setup is less than the property of UG for the initial setup. UG final is less than UG initial. So that's just what this formula means. Now, if we combine both equations that we obtained, like WG is equal to negative delta UG, and we combine that with the formula I gave you about UG, you will arrive at this other important formula that WG is equal to GMM over R final minus GMM over R initial. Well, let's not dive into what that means. Let's just proceed to the derivations. Before the derivations, this is the first thing I would like to derive and to prove that the work done by gravity is equal to the negative change in potential energy. In this picture, an apple falls down from not from the tree, but from a height similar to the height of the tree. We say, if you remember, that the apple has a potential energy called mgh. Although, to be honest, that's not really correct. You don't say an object has potential energy. We say that the apple and the earth system has potential energy because potential energy is a property of a system. Okay, so we say that the apple earth system in this case has an initial UGI of mgh and final UGF of 0 if it falls down to the ground. We set h equals 0 at the ground, right? That's what we usually do. And technically, we say that the 0 reference line where the gravitational potential energy 0 is set at the ground. So that term, 0 reference line. So the external force can change the position of the apple with respect to the Earth, thereby changing the potential energy of the apple-Earth system. In other words, the external force added energy to the system. When an apple is on the ground, we say that the potential energy is 0, right? But we can do something to make the potential of the potential energy of the system non-zero, and that is we apply an external force when we lift the apple up so that the potential energy is no longer 0. So that's what we do. Here, as you can see, the apple is on the ground, so we apply an external force. And we have to be careful that the external force that we apply is equal to the gravitational force. Why do we need to do that? We need to do that because we don't want the apple to accelerate. We don't want the apple to accelerate as it goes upward because we want to keep the kinetic energy constant. We don't want to deal with changing kinetic energy because for this particular problem, we want only to deal with changes in potential energy, not changes in kinetic energy. So that's the reason why we want to keep the external force equal in magnitude to the gravitational force. And now we calculate the work done by the gravitational force, and the formula is Fd cosine phi. Our F, of course, is the force of gravity, and our displacement is an upward with a magnitude of h, and the angle between the displacement and the force is 180 degrees because they are complete opposites. Our gravitational force is downwards, but our displacement is upwards. What we actually get is negative mgh. So our UG final in this case is when the apple is above the earth, that's mgh. And our UG initial is when the object is on the ground, that's 0. So our change in gravitational potential energy is UG final minus UG initial is just equal to mgh. Therefore, since we got Wg, or the work done by gravity, is negative mgh, and since mgh is equal to delta Ug, then we arrive at this interesting result that gravity causes a negative change in this property called Ug. We are going to use this to derive the universal gravitational potential energy. Remember, this is a throwback, so this is not the formula. MGH is not the formula we are interested in because this only applies in places where the gravitational acceleration is constant, and that would be near the surface of the Earth. We're dealing with more general cases when we are dealing with the Earth and the Moon, or practically any object with mass we are dealing with in general. We need a more general formula for gravitational potential energy. And to do that, it still involves moving objects around and calculating the work done by the gravitational force so that somehow we can come up with a formula for the potential energy. In this case, we have two objects. Sorry, the blue object and the orange object. And think we're keeping the blue object stationary and we're applying a force, an external force, so that we can move the orange object to the right. But before that, I hope you remember that since these two objects have mass, they are attracted with a gravitational force. So how do I move the orange object from R1 to a new distance of R2? Because we want to have a change in UG. Simple. What we do is we apply an external force. And this external force must be the same magnitude as the gravitational force. Because we want this orange object to move to this new position at constant velocity so that there are no changes in kinetic energy but only changes in potential energy. But we're calculating the work done by gravity. The work done by gravity in this case is the integral evaluated from R2 to R1 of fg.dr. And we are using this integral formula because gravitational force is not constant. It's, in this case, actually decreasing because it's getting farther and farther away from the blue object. Here there's a dot product involved. Oh, this is wrongly placed. So we need to define the r hat vectors. As you can see, the r hat for fg is negative r hat, and that is because, where is that pointer? Okay, right? I'm looking for the pointer. Oh, anyway, the where was I? Yeah, the radial r hat, the radial unit vector is negative r hat for fg because it's radially inward. But the radial unit vector for our little displacement dr is positive r hat because it's radially outward. So rearranging terms, we get the negative fg times r hat dot product of r hat, and I think I described this in the previous video, which I deleted, that r hat is equal to 1 because they're in the same direction and they both have a magnitude of 1. So we are left with negative fg. Fg, of course, has a formula gmm over r squared. Taking out these constants, negative g, m, and m, we get here the integral of 1 over r squared dr, which will give us a negative 1 over r, so the two negatives cancel, so this becomes positive. We are left with an expression, this gmm over r2 minus gmm over r1. So just to emphasize further, this is the formula for the work that gravity does when we change the orientation of the masses using an external force. R2 is much greater than R1. So what we are actually doing is we are changing the gravitational potential energy of the system. There is a change because initially the objects are closer, but by applying an external force, the objects are now farther apart. We caused a change because we do know that from our throwback, the work done by gravity is causing a negative change in the gravitational potential energy, or UG2, or which UG2 stands for UG final plus UGI. So where did I get this? Well, negative delta UG is equal to negative UG2 minus UG1. And so I just distributed the signs. You'll get this. So, but take a look at this. We're now comparing two expressions, this expression and this expression, seeing parallels. First of all, we see that the terms correspond with each other, right? But they correspond in such a way that one is the negative of the other. UG2 corresponds to GMM over R2. The only difference between them is this negative sign, and UG1 corresponds to GMM over R1. The only difference between them is the negative sign. Therefore, actually, since they are equal, they're all both equal to WG. Therefore, UG1 is equal to negative GMM over R1, and UG2 is equal to negative GMM over R2. And in general, UG is equal to negative GMM over R. After such a long process, we finally derived the formula for UG. So there's another proof as to why UG is always negative. And I'm going to explain this graph a little bit. Remember that when we had a throwback and then we said that the H equals 0 at the ground, for this new formula that we have, um, negative negative GMM over R, when can we make this equal to 0? So when is UG equal to 0? And we can only make this equal to 0 if R is equal to infinity. Yeah, because if we divide this expression by infinity, we divide GMM by infinity, that becomes 0 because the numerator is divided by a very large number. Infinity is a very large, it's an infinite number. So at r equals infinity, UG equals 0. So we're saying that we're putting our 0 reference line at a distance infinite away from, um, or we're treating both objects as an infinite distance apart from each other. So in this graph, at r equals infinity, we reach 0. So here clearly we are dealing with um, any infinite, any r's less than infinity. This is gonna asymptotically reach 0. and it can go towards infinity before it reaches zero. So all other values of r we are that are less than infinite, we are treating their corresponding UGs as below zero. So that's why we have negative sign. So again, UG is always less than zero, but the change in UG can be positive or negative. So that's the important thing. Oh, that ends my video. Thank you.